So this is example 4b. It's actually the same numbers as 4a, except the big change is instead of being a frictionless ramp, we now have friction with these values of the coefficients of friction given. So what I'm actually going to do is transfer some of the numbers from example 4a into here that I already calculated. For example, I calculated that the gravity pulling down on the lowercase m block was 9.8 newtons. And I calculated the x component of gravity pulling down on the capital M block was 33 point... I kind of forgot here. 0.9, I believe, newtons. Okay, so that was information from 4a. Now, the difference here is going to be there's friction. So that would apply to the capital M block, and which way would it point? So right now the block is at rest, it's not moving. If it were already moving, it'd be a lot easier because the friction's always going to point in the opposite direction that it's sliding. But what if it's not sliding? Well, then friction's going to point in the opposite direction that it would attempt to slide. And based on example 4a, if there was no friction, it would slide down the ramp. So that means friction, if we add friction in, that would try to resist that, and friction would be pointing up the ramp. So now I got to throw that detail in there. So that's going to reduce, or that's going to counteract some of that 33.9 newtons. And is that going to actually cause the blocks to not even move at all, right? Because if static friction is big enough, then the blocks may not even move at all. So what I'm going to do is calculate the maximum static friction on the block capital M. So right now the difference between 33.9 and 9.8 is 24.1. Okay, so far the capital M block is winning by 24.1 newtons. And we'll see if that's enough to overcome this maximum static friction as well. Okay, so static friction it has a formula. It's the coefficient of static friction times the magnitude of the normal force. And the magnitude of the normal force, so now we have to bring back things from the ramp questions from the previous lesson. The magnitude of the normal force is equal to the y component of gravity, FGY. So this equation becomes mu s times FGY for the capital M block we're talking about on the ramp. And FGY has a formula. It's mg cosine theta. So that's how I'm going to calculate the maximum static friction. So 0.40, mass is 4, 9.8. 9.8 cosine 60 degrees. That's a nice angle for cosine. Cosine 60 is a half. All right, I'm going to calculate this up. And I'm getting 7.8 newtons. Okay. Therefore, I'll add it in my diagram here. Well, no, I won't actually. Therefore, I think this block will still slide down the ramp, because that 33.9, that's bigger than 7.8 and the 9.8 added together. So I'll write a little statement here. The 33.9 Newton force, or I won't call it a force, because it's just actually a component of gravity. So I'll say component overcomes both static friction and gravity of m, lowercase m. It beats them both combined. So therefore, the system will accelerate. With capital M sliding down the ramp. Just going to add one more digit, 7.84. That's coming up on my calculator. I'll just underline the 2 sig figs it's supposed to be. All right, so it will accelerate down the ramp. So what I'm going to do is try to figure out how much that acceleration is. So as soon as it starts moving, static friction turns into kinetic friction. So I'm gonna have to calculate kinetic friction now, which will be mu k times the normal force. So all the calculations here are the same, except instead of 0.40, it is 0.20 times the normal force. So I'm just going to look to the left there and realize that, well, these are nice numbers they give us. 0.20 is actually just half as much as 0.40. So when I do all the work, my answer is just going to end up being half of 7.84. So I'm just going to take that shortcut. I'll just divide that by 2, giving me 3.92 newtons. Okay, so that'll be the amount of kinetic friction. So when I go to calculate the acceleration, I'm going to treat everything as a system. Of mass, add the two masses together. So that's 5 kilograms in total. So this entire 5 kilogram system has a net force of, it's going to end up being, in terms of magnitude, the 33.9 newtons, which is pulling the block down the ramp. Subtract the kinetic friction on it, 3.92 newtons, and also subtract the 9.8 newtons that the lowercase block is kind of pulling the other way on. So that'll be the overall net force. So coming up with 20 newtons, 0.18. And now Newton's second law will help us get the acceleration. It'll be net force divided by the total mass of the system. So 20.18 divided by 5.0. Well, 4.0 when I rounded to two significant figures. All right, so actually not too much friction there. I believe the answer to 4A was 4.8 meters per second squared. So with this friction here, the acceleration is not as much, slightly less. There's not going to be too much friction because the ramp is really steep, so that actually makes the normal force pretty small. So this seems like a reasonable answer.